Hello, my name is Nick Ware with Alpha Milling Company. I appreciate your interest in joining us on this 3D milling demo. Originally, this was scheduled to take place on site on Northwest Parkway, but due to inclement weather, we had to cancel that and move everything online. Just for reference, you'll see a change in my attire here towards the end of the video. The actual demo took place a couple days ago. And there was an issue with the recording. In fact, I forgot to hit the record button. So I am going to re-record the first portion and actually do the demo of what I did a couple days ago. Fortunately, we were able to get all the Q&A. So at some point when I'm done walking through the basics, I will flip over to the Q&A portion. And if you're viewing this demo later on, then you'll be able to take part in the Q&A. And of course, you can always reach back to us, any of us at Alpha Milling, and ask any questions, start a conversation anytime you'd like. We'd love to have that conversation with you. Okay, so I'll get started. What exactly is 3D milling? You may often hear it or also hear it called automated machine guidance. So basically all that is using a computer model and uploading that information into the rotomill. And then the rotomill now actively controls its own elevation or depth of cut. So traditionally, you'd have a groundsman or the operator with a control box in front of them, and they'd be manually punching in the buttons to move the machine up and control the depth of grade manually. Automated machine guidance, or 3D milling, takes that manual process out and has the mill automatically cut to whatever's shown in that design model. So there's effectively two main ways of doing 3D milling. One is using a total station type reference. So you have a static reference on the side of the roadway in the form of a total station, and that communicates directly with the mill. And you actually have several of them set up along the roadway. And I have a video of some actual footage that we took a couple days ago that was on site on Northwest Parkway before the weather went bad. So I'll show you that here shortly. But going back to the total station method, as I mentioned, you'd have several total stations strung out along the roadway, and those communicate directly with the mill. And when the mill communicates with that total station, it's able to determine its spacing horizontally and vertically, or I guess more accurately, latitude and longitude, and also its vertical elevation. So there's three axes that the machine can now determine by communicating with the total station. And what's interesting with this method of 3D milling is that it doesn't really matter what's on the roadway. Maybe there's something in the way or some pile of asphalt or something that got in the way since the model was designed. Well, it doesn't really matter, because what the model is doing in this form of 3D milling is it's telling the machine, you need to be cutting at this elevation. Right now you're here, you need to get to here. And so it doesn't matter what the roadway is, all the mill is going to do is cut until the total station tells it it's at the elevation prescribed to by the model. The other way of thinking about 3D milling, or the other way of doing it, performing it, is more of a GPS type system. So in this case, there is a GPS receiver that's set up alongside of the roadway, and all this does, the mill has its own GPS as well. But the station on the side of the roadway communicates with the mill and just gives it more accurate GPS readings. So all that does is clean up the GPS signal effectively. So the mill is still using its own GPS locator to tell it where it is, latitude and longitude, or spatially along the roadway. It does not tell it its elevation, whereas the total station did. It's all, and going back to the total station, it has to be calibrated every time you set it up. And using a surveyed reference point, so it knows what elevations it's at. When we go to the GPS system, what's telling it its elevation is the existing surface. So rather than using a static reference as like a total station, now using the GPS system, we're using the existing roadway as a reference. So the GPS tells the mill where it is, lat and long, and then it just looks at the existing surface and says, okay, I know at this location, I need to cut 2.5 inches. So the drawback, actually, let's say the benefit with the GPS system is it's quick and easy to set up. quicker and easier to set up. The downfall is that if you make the cut, now you've removed your reference. If for whatever reason you need to go back and recut it, your reference is gone. You've already milled it up. So you'd have to basically resurvey it, not resurvey it, but get new data and figure out where you're at, where that machine is, and what the new depth needs to be. So that can be cumbersome and difficult. Whereas with the former method, the total station method, it does take more effort to set up because you've got to calibrate all those total stations to their existing elevation. But once you cut, if you have to go back, it doesn't matter. Because as I mentioned, you're not using the surface of the roadway as a reference, you're using that fixed reference as the total station. So let's say, for example, I cut to here, and then I went back, I checked grade, oops, that was wrong. Something was messed up with the calibration of the total station or something like that. So we go back again, recalibrate it, no problem. It's using the total station as reference. Now it knows it needs to cut a little bit further to get to what the model prescribed. I'm gonna pause one moment.
This conference will now be recorded.
Okay, so let's talk a little bit about that model and how you come up with that data. The old-fashioned way, so to speak, or the traditional method, maybe more accurate, is just a typical survey. You go out and take survey points along the roadway, see what those are. You've got enough, you need to take enough points to get a good, accurate model, but you can certainly do that and then go build a model later on. The other way, some of the more advanced techniques, for example, would be like LiDAR systems, and some of them are even truck mounted. So you can go take a scan of the roadway at highway speeds and gather a whole lot of data. So there's numerous ways of coming up with this data, but once you do it, you take it into a modeling software that's designed for that purpose. You can see now we know what our existing elevations are, what our existing roadway looks like. We can model in what we want it to be. Maybe we change cross slopes, maybe we change longitudinal smoothness, maybe we change a super elevation, whatever you want. All that's done in the software itself. And then once you're done, you've got a surface model of what you want the road to look like, what the finished product should be, and then you can go take that into the machine and start milling. Obviously, when you do that, one of the factors to take into consideration is what is the thickness of the overlay going to be, whether it's concrete, asphalt, whatever's going down. So then you just simply adjust that in the model. If we're going to put 3 inches of new asphalt on top of the roadway, then we just have to make sure we cut 3 inches lower than what final surface elevation is going to be. Okay, so let's talk about benefits and why you should use 3D milling. Well, the first one's the obvious. That's more smooth roadways, increasing smoothness, improving your IRI. Obviously, that's a benefit to the owner agency and, of course, the general public. Longer life of your roadway, and certainly happier end users that are traveling on that roadway. When you think about smoothness, I mean, typically the mindset is when you pave it, let's say you've got a 30-foot ski on the paver, every time we do that, we're going to get a little bit smoother. Well, you should certainly think about the mill as no different than doing smoothness with a paver. In fact, it may be more accurate because you're no longer relying on an averaging system. Whereas with a 30-foot ski, it's taking an average of that distance and sort of smoothing out the hills and valleys. With a 3D model, there is no averaging. It's all exact. Whatever it is at that point, every inch that machine moves along, it might be slightly adjusting its elevation. So it's very direct and accurate elevation control rather than just sort of a smoothing operation, which is certainly capable of doing that on mills now, just like you are pavers. But the 3D gives you a point by point by point specific elevation at which to cut. As I previously mentioned, one of the other benefits, adjusting your cross slopes. If there's a lot of things you need to change, you've got really complicated elevations and changes in elevations, obviously you can do that all in the modeling process and then put it into the machine. You don't have to rely on someone to manually chase those grades and do the best they can and get as close as they can. You can do it exactly as you'd like. Parking lots, drainage issues. Same thing there. You can certainly survey the parking lot, and then rather than trying to mill a little bit out what looks like it might drain, then using a smart level or shooting a few grades, just go out ahead of time, grab those grades, again, whether you use a traditional survey method or a faster, maybe a truck-mounted LiDAR method, something along those lines. Either way, you shoot that grade ahead of time, and you go put your mill on the job and mill it to the exact specifications that you want to make sure that drainage exists in a parking lot. Quantity control. If we know what the model looks like ahead of time, then the owner agency is going to know exactly how much material is coming off the project. And consequently, if we're using a 3D milling project, now rather than try to correct smoothness with the overlay, i.e. thin areas on hills and extra material when there's a valley, all that's done ahead of time with the mill. And now you can have a consistent thickness overlay. There's not that question of, wow, how much extra or overrun are we going to have on that material because of all the holes that we've got to fill, the valleys we've got to fill, or the converse of that, are we going to have short pours? Are we going to have thin areas that we just have to deal with because we're trying to smooth everything out? If you mill it ahead of time and do your smoothness with the mill, then you can have that thickness overlay on top. And again, coming back to the quantity control aspect of sort of things, we know what our yield's going to be. Obviously, we should be very close to spot on what that yield's going to be if we know that it's going to be a consistent thickness because all the bumps and hills and valleys have been taken care of ahead of time. Let's see, one of the other things that's really interesting about this technology is it can more or less eliminate or reduce the need for on-site inspection. When we go behind the mill and check our grades, again, I'll show you a video of that in just a moment, but we can actually send that data directly to the cloud. So you can be monitoring the progress of a project on a highway and see those data points as they come in. As the mill goes along down the roadway, there's a person standing behind the mill with a rover checking those grades, and that data can be sent instantly to the cloud, thus, like I say, either reducing or eliminating the need for someone to be there on site and verifying those grades. The last piece or another benefit is that you can use the same model for both milling and paving. Obviously, for the purpose of this demo, I'm focusing on the milling aspect, but the same exact technology exists for paving, and you can use the same hardware, the same total stations, and of course, the same model to upload into the mill and upload into the paver. So even if, in our case, we're usually acting as a subcontractor to a paving GC, we can all share that same data and share the same hardware and improve our efficiency, and both of us using that same model. Okay, I'm going to flop over to the video real quick, so bear with me, and I'm going to pull that up and see if I can't share my screen. One moment. Okay, so I'm going to go ahead and play this video. Nothing out of the ordinary here, obviously a typical milling operation, but this is 3D milling on Northwest Parkway. I'm going to pause it for a moment. You can see here on the top of the mill, the yellow mast. So that is the receiver for the total station. One of the things using this method, and this was the first method I described with 3D milling, using the total station on the roadway as a static reference, is that total station needs to have line of sight. It uses a laser type system that communicates with that receiver. So as you go down the road, if there's something in the way, then you may have to switch over to another total station or stop and move that total station. But nonetheless, in this particular instance, it must maintain line of sight with your reference point. Going back to the other method when I talked about a GPS-driven system, there isn't anything to maintain line of sight with other than the satellites, but that's obviously using a radio or frequency. And then I did mention the GPS station on the side of the road. That also uses radio. So that can extend a long distance and you do not need to have line of sight with that GPS. But you run into other issues. For example, if you're going underneath an overpass or a tunnel and you lose GPS signal, then you're going to have to do manual grade control through that section of the roadway. Okay, moving on. So as I mentioned, the yellow mast. We'll switch over here and see some of the hardware next. Okay, so we can see the total station here, this big yellow guy. And then we usually set those up about every, call it 250, 300 feet apart from one another as they go down the roadway. They can be stretched out as far as 500 feet away from the mill. So in theory, you could have 1,000-foot section where you're tracking one for 500 feet, then you switch to the next one that's 500 feet away as you track towards it. We just don't like to spread them out that much, just for that whole issue of line of sight and just simplicity. It's easier to move to the next model when they're a little bit closer together. And so the way this works on this project, we have 5 total stations set up. And once they're no longer using the one at the start, after they've gone down the roadway and no longer need it, then we'll run back up there, grab it, and leapfrog, take it down to the other end. So the milling operation should be continuous, and you just have to leapfrog those total stations as you go. All right, so moving on. All right, in the next set we should, so you can see a gentleman right here doing some data collection. I think in the next clip we'll have a closer up view of that. So when we get to it, I'll speak on that momentarily. Nope, I must have missed it. So I'm just going to jump back. So this gentleman here is the data collector. See, he's holding a rover and he's checking the grade instantly behind the mill. So as soon as we cross over that point, he's checking grade. If we have it set up that way, that data would be uploaded to the cloud. But more so, even though we're not saving that data or uploading it, we're checking the grade to make sure that we don't need to do any minor adjustments. As we go on throughout the day, sometimes temperatures, as heat increases, it can change the way your total stations are calibrated. As the teeth wear, you might see a slight change in elevation there. So as we go, we need to make minor little adjustments to make sure everything stays accurate. And that person following the mill with that data collector is what's enabling us to do that. All right, so I'm going to jump back ahead to where we were. Just another viewpoint of a total station way back there. As the mill's coming down, here's our next one. So just trying to demonstrate that, you know, as we go from one to another, we just bounce from gun to gun. And the person on the data collector needs a gun too. So they need a dedicated total station so they can transmit their information that they're checking behind the mill. Right, here we have one of the data collectors, or sorry, one of the total stations. And these are robots. So as the mill goes down the road, they pivot to adjust. So right now the mill's passing by this total station. And as it's tracking that receiver, it's constantly sending data back and forth, knowing that I need to track it down the road. So it is a dynamic moving robot that has to move along with the mill. So that's how you're enabled to maintain line of sight communication with the mill as it travels down the roadway. And there's just a shot back looking at the mill as it's cruising down the road. Okay, there's my video that I was looking for. So that is my data collector, kind of the close-up of him. He's got a little tablet there as well. So he's got the model loaded in there and he's able to check, is this point accurate? As long as it's communicating with that total station, it knows where it is. It now knows its elevation and it can tell you, is it correct? Is it a hundredth of a foot too high or 2/100ths of a foot too high? Okay, so here's the roadway after we've milled it. So I just wanted to show this just so you can kind of see some of the variable depths. Started out at 0. We're climbing or cutting a little bit deeper as there is a bump in this section. And in a moment, as we get a little further, it'll pan back out, come back up to 0. So basically, you can just see that, yes, there's a variable depth milling and it has nothing to do with anybody pushing buttons on the side. It's using its model to create that variable depth mill. So there we go. It's feathering back out to 0, and then we're terminate. Now we're flush with the existing asphalt next to it. Okay, that's all I've got for video. So I'm going to flop back to my presentation. Bear with me for one moment. Okay. So I just want to talk a little bit about other applications. So obviously we know we can use 3D milling for the purpose of an upcoming asphalt or concrete overlay, but there's some other options as well. I did talk about parking lots, which isn't so much another application, but rather another place that it's utilized. But for example, surface treatments. So if we think about some thin lift overlays or different surfacing, whether it be a chip seal or a micro seal, or slurry seal or something along those lines, where you just want to do a thin lift pavement preservation technique, but the road's got some bumps and grade issues. So we can use the mill, to correct those grade issues prior to that thin lift application. In this particular case, in these thin lift overlays or surface treatments, we'd want to use a micro mill, which is, if you're not familiar, it's a mill, but it has a lot more teeth, so you have a lot finer finished surface. It doesn't have as much grooves and ridges as a typical milled surface does. But in this case, we can use a micro mill, couple it with a 3D milling system, get rid of all those issues, grade issues or surface elevation issues, and then you can use a thin lift overlay or a slurry seal or a surface seal, and not have to worry about any sort of weird grades that get reflected through the new surface. Let's see what else. Cold in place recycling. If you're a fan of cold in place, when you do that process, the cold in place train does not have a lot of flexibility for adjusting grades or longitudinal issues. So they can only make minor adjustments. Otherwise, you start running into issues with the cold in place, not having consistent thickness mixes of that cold mix. So you would go through with the mill ahead of time, make any grade corrections, and then follow that with your cold in place process. Full depth reclamation, you can also potentially use it after that FDR is completed, after it's been shaped and compacted, and then use, again, a micro mill with a 3D system to trim those edges and get you to the final grade that, the exact precise final grade that you'd like to be at before putting on whatever overlay it is you're putting on top of that FDR. Really, the way to think about it is you use 3D milling anytime you want some very specific grade control. Anytime you want to make any, not necessarily grade control, but grade corrections. So anytime there's that issue, 3D milling has some way, form, or fashion of incorporating those adjustments. Okay, I'm going to stop the presentation here. In the next section, which I recorded a couple days ago, I'll talk a little bit about how agencies can get that put into their program, and then we'll go through the Q&A. Thank you.
Nick, I got a couple questions for you.
Okay.
Do we have any metrics that show right improvement before 3D milling and after? And second question, do we have any metrics that address how much more life it might give to the roadway from providing a smoother ride?
Great question. Dan, if you wouldn't mind jumping in. Dan's been doing this for a while and he's more familiar with the data that's available out there. So if you could jump in, Dan, and help answer that, that'd be fantastic.
Yeah, it's I guess as far as it's hard to quantify that, because if you're trying to run an IRI on a milled surface, you won't necessarily get accurate data out of it. But when you start looking at comparing our milled surface to the modeled surface, and we could track that, like Nick said, in the cloud, you'll see that our tolerance is less than 1/100th. And we've been able to do that for on certain projects, 99.4, 99.6% of a job, the tolerance is less than 1/100th. So it's very accurate, very smooth. And so that really helps out a bunch. And then I guess as far as extending the life of a road, there's been lots of studies at how smoothness affects the life of a pavement and also the life of all the vehicles that travel on that pavement. And so, I mean, if a smoother road will definitely help out any type of those type of applications. So I would say if you want some more information, we'll definitely get that to you.
Thanks, Dan. I might add to that. We obviously know that smoothness can affect can extend the life of the roadway. And sure, could you go in there and have a really good milling job and a really good operator and labor that contribute to that? Absolutely. And that's going to extend the life of the roadway. And same thing on the paving section. Can you have a really good paving company that extends the smoothness? You bet. And then consequently extend the life. So what it comes down to is we know that smoothness extends the life of the roadway. It's how you get there, right? And obviously, if you can have a form or a method that gets you extremely accurate, then you can ensure that you're going to get to that point, or be significantly more likely that you'll get to that point. The other piece I was going to mention with metrics, just lost my train of thought. I'll come back to that, but I had one more thing I wanted to throw in metrics, but I'll see if I can't remember what I was just going to say. But along those lines, what do we do next? If you're an agency or you're a contractor, okay, great. This is something that makes a lot of sense. How do we get that deployed into our projects? Well, from the contractor's perspective, you can do it anytime you want, right? If you're really concerned about meeting maybe an IRI specification or smoothness specification, you can think outside of the box and say, you know what, it might be worthwhile to build this model to ensure we get there. And that just basically takes getting that data via survey or like I mentioned, LiDAR method or something else that gets you the data points you need, build the model. And it doesn't necessarily have to be complicated and time consuming to build that model. If you have the appropriate data, you can do it fairly quickly, in a day or two, something along those lines. It's not necessarily a months long project or anything like that. It could be if you want to add all sorts of other, issues, who knows what, just, I guess different, changes in grade or something. I don't know. You can make it as complicated as you want, but if you're just going from a grade control perspective, it's not a particularly difficult thing to do. So again, if you're a contractor, you might think about it as, a parking lot or a roadway. We have a lot of these grade corrections, or we have a lot of drainage issues or slope issues or something like that. We can employ it at any time. We just need to get out there and build a model for it, a couple of days or, a week or whatever it may be in advance. If you're the owner agency, what you've obviously got to do is decide how you want to put that in your specification. Do you want the contractor to be responsible for developing the model, performing the survey? Or as an agency, do you want to do it? So go out and do the survey ahead of time and say, okay, GC, from a bidding perspective, this is what we've got. This is what we want to get to. Here's the model, or here's the surface design. We'll provide that for you. You need to make sure you have the equipment to go and perform it, right? In that regard, it can be beneficial for an agency to say, okay, look, we've done the work. We know what it needs to look like. We have the model that shows exactly what our elevations will be, and consequently, you calculate your IRI from that point. We know what it wants to be, what we want it to look like. Now, contractor, you go build it appropriately. And either way, whichever way you go, you need to obviously have a specification in there that says, okay, this is how we want it to perform, or you need to use automated machine guidance to achieve that. And we can help with that. So Midstate was instrumental in designing that specification for MnDOT. So MnDOT has that spec. We can certainly talk through it and help you as an agency design it, or help talk through the issues of maybe some changes you want to make here and there. Obviously, it's a benefit to us. I mean, we're looking to make $1 by putting this out there, but we're looking more so to improve the industry. We very much have the mindset that high tide raises all boats, right? So if we can help an agency develop the platform and develop the specification and figure out how to get this employed, we may not get the project. Someone else may, but obviously that's what we're hoping for. And just as an overall industry improvement, if we can make our roads last longer, be more accurate, be more efficient, and extend the life and make the agency happy and the customers, or the end user, i.e. the public, happier, then we're happier as well, and it's going to benefit us in the long run. So we're more than happy to have a conversation that's not a sales pitch. Let's just talk about specifications. Let's talk about what makes sense for the agency and just sort of help you through that guidance. Obviously, CAPA is a good resource as well, and various agencies around the country. If you may, MAPA, there's several others that have a lot of exposure to this, when we can certainly put everyone in place with the right professionals, the most experienced folks that can help you get there. Let's see. I think that sums it up for me. Dan, anything else on your end, or anything out of this that you wanted to throw in?
No, I think that really covers 3D milling. And like you said, Nick, I would like to help anybody out in that effort in any way. Just look at us as a resource. Call on us whenever you need us.
Absolutely. And before we hang up, let's take a few minutes, as long as we need to. If there's some questions out there, go ahead and jump in.
Yeah, I have some questions. This is Grant Bloom, City of Thornton. I'm curious, in, say, the metro area, how prolific is the use of 3D milling? As in, say, in your company, how many crews do you have who can do that? Like, I guess I'm curious, perhaps as a percentage, like how many projects are using it? Because I'm sure it's very application dependent. And then, like, what is the capacity to do it as we want to perhaps move more in this direction? I have more follow-up questions, but I'll let you answer that one first.
Sure. Okay, so to answer your question, in the Denver market, it's not prolific. We have one machine equipped for it. In Minnesota, for example, it is prolific on the state level, and it's starting to, drift out into counties and private work and that sort of thing. Like I mentioned before, in Minnesota, we performed about 1 million square yards this year. In Denver, there is some. Asphalt Specialties performed a 3D milling project on an airport this year. I believe it was Boulder Airport. There's been a few other here and there. It's not prolific, and it's there. It's just that education piece, right? Agencies, engineers, that sort of thing may have heard something about it, but just don't know a ton about it. That's obviously the intent of why we're here today, but to get that word out, because it does make sense and it does work. Where we're doing our project is, I'm pretty sure I mentioned it, but if not, we're on Northwest Parkway. So that's kind of one of the first that we're starting to see on a local roadway as opposed to an airport application. But like I said, it covers the gamut. You can use it in a parking lot if that makes more sense. And I mentioned one machine is what we've got equipped with. So as far as capacity goes, you can use that machine anytime. It takes maybe a couple hours at most to bolt the mast back on, because we don't leave it on there. It might break and it's expensive. But the internal components are always there and they're always ready to be turned on. So you hook up all the components, bolt on the mast, and you're ready to go. Obviously, the only time constraint issue is making sure that you have that model. But once that's there, we can do it tomorrow. That answers your questions, Grant.
Sure. And then I guess the other piece of that capacity equation is the personnel who have the training to be able to effectively operate it. So between equipment and personnel, which one of those would you say is more the limiting factor?
The limiting factor would be personnel. I mean, once you've got the equipment set up, that's a piece of cake. You've got to have the knowledge level to be able to set up the total stations and make sure everything's communicating appropriately. So internally, we as a company, Brian Hill just jumped on. He's sort of our guru and our man in charge when it comes to our internal ability to self-perform this. There are other resources. For example, Luke, who's on the call, is with SciTech Rocky Mountain. They can do it as well. So if we're in a bind or we've got two projects going, one in Minnesota, one in Colorado, obviously we intend to train more folks so we have that capability to do multiple at a time, but we can borrow their services. They're the ones that sell this product. They know about it. So we can hire them to come do the total station and the, I guess if you want to call it site preparation or calibration type work, and then we can go do it. It does require a little bit of extra knowledge from the mill operator, the ground person, whoever the data collector is behind the machine, but that's a much smaller learning curve. Once you understand it, once you understand what's going on, that's easy. So we have a lot of folks internally that can handle that. It's just a function of making sure that we've got the knowledge to make sure that the total stations are set up and calibrated appropriately.
Okay, yeah, that makes sense. And then have you seen, or I guess have you kind of envisioned what kind of the natural break point happens to be where this becomes financially advantageous? Because I mean, thinking about it, I'm looking at it from the owner's perspective. I would want to go in this direction primarily either because we will realize a cost savings or because the scope benefit outweighs whatever cost differential there is. So are you seeing any natural break points where it seems like, yes, this becomes a great candidate for either in terms of project length or just how often, if a road just has like ridiculous drainage issues, those are the candidate projects. Could you speak to that?
Yeah, so, and Dan, maybe you can help me jump in here, but I have not yet seen kind of what and if there is a break point. Obviously from my world, it's relatively new and we're getting that information as we go. But Grant, to your point, obviously if there are significant grade issues, then yes, you want to employ it to make sure that you get those grades corrected appropriately. It's not a significantly more expensive process. I mean, basically what we need to do is, from a contractor's perspective, is cover the cost of the equipment and recoup that over time. That's the big driver, and it is expensive equipment, but we can break that out over several years. So it's not like double the cost of milling, and don't hold me to this when we put out numbers at some point. But you know, you could maybe expect call it a 20% increase in unit rate, which obviously in the, you know, world of a contract, the milling is a relatively smaller portion. So it's not a significant nominal dollar increase, but there is some adjustments to make that. So if you're just doing some, you know, edge mill in a residential zone where grade control isn't a significant issue, yeah, it probably doesn't make sense to use 3D milling. You know, why bother, so to speak, right? But anytime that there is some tighter tolerances, or you expect out of us, the contractor, increased smoothness or grade corrections, then I would certainly look at employing that. Dan, can you jump in? Have you ever seen anything along those lines where there is a breaking point, or when it might make sense to move from one to another?
We haven't really seen anything that's a definitive breaking point, but I would say it's project by project is what we're looking at, and how you want to analyze whether or not you want to use 3D or not. I mean, obviously, if it's a project where you're seeing ponding issues that you want to correct, or you have cross slopes that are, you know, suspect, that have flattened out over time or changed, those are great candidates for 3D milling. Anytime you're looking at maybe needing to do a bunch of leveling course, right, on a job, it's definitely gonna be cheaper for you to mill that section out and smooth it out than it will be to do a leveling course. So it's really on a project by project basis, right? And, you know, ride quality definitely on a road with higher speeds is much more important than probably a city urban type street as well. But in that urban setting, if you just have in place curb and gutter and fixed elevations, and you want to improve the ride as best as you can and get water diverted where it's supposed to be, it's a really great application too. So there are a ton of applications, but I've not seen a breaking point there where it makes sense. But I know, okay, if you do have any questions about pricing or something else, would this be a value to you or not, just give us a call and we'll let you know kind of what we think that cost would be, and that'd be something you could add to your calculation and your planning process.
Gotcha. Yeah, that makes sense. I did have one more question, but I lost it in the process of listening. One, I guess, just kind of feedback thing. If you don't already, and if you do, I'd love to, if you could point me in that direction. But if you had like perhaps like a vignette, like a story of, you know, we used, and maybe they're developing this with Northwest Parkway. You know, here were the issues of the project. This is how we use 3D milling to correct those, and here are the metrics that, you know, really showed that 3D milling was worth its weight. Like we accomplished this smoothness criteria, or we corrected all these ponding issues. Because I feel like, especially as an owner, I can look at those situations and be like, oh yeah, such and such road is exactly like this. This would be a great idea. Just, I guess, as a general feedback.
Yeah, absolutely. We'd be happy to, Grant. Well, we can send that to everybody. We do have some success stories. There's some with, you know, that are outside of our company as well. So we'll dig into those and distribute those for you.
Okay. Yeah, and I just remembered my other question, then I'll get off the.
Can I jump back in on that one, Grant?
Say again?
Can I jump back in and add to one of your questions there?
By all means.
Something to take into account is the putting the consistent mat down. We're developing a consistent mat here, so your quantities will offset some of those costs. You're virtually eliminating any overbuild here. So that's a cost savings that's going to help pay for the little bit of extra when we 3D mill. So you got to take that into account too.
Thanks, Brian.
You bet.
And yeah, I would just add to that too, that so if you guys are paving with a consistent asphalt thickness, you're going to see better density numbers throughout the length of your job as well, right? Because as depths vary, and if you're using the same rolling pattern, then your densities can vary slightly. So the whole process is just going to help out with lots of consistency.
And that goes back to quality too, because if we build a consistent mat over our milled surface, failures don't tend to come back to us because it all falls back on the engineers. They can estimate the longevity of that mat better if it's more consistent. Correct me if I'm wrong, Dan. I'm not an engineer.
Yep.
Oh, no, you're right, Brian. All that ties together.
Great. Yeah, that all makes sense, and those are definitely really great things. I did remember my other question, and so probably illustrate my ignorance. The array of teeth, like transverse in the transverse direction on a milling machine, because I gather that 3D milling is not changing the machine; it's just augmenting it with survey technology. How much can you as you're going across the machine? Can you vary the height of those teeth, or is it effectively a straight bar from one end to the other?
That's a good question that applies to any milling application, I suppose. They can vary. Gosh, I don't know, if you had really bad teeth on one side and really good teeth on the other, you could get an 1/8 of an inch variation or a 1/4 of an inch, even if it was really obscene. So that's a possibility. But that's in effect why, for particularly with CDOT, is why there's a surface texture specification. You want to make sure that your pattern's appropriate. The one thing you would see, Grant, with that is if there was some sort of weird elevation issue, your pattern would look ridiculous. I mean, you'd notice that instantly because you'd see it in what the asphalt looked like behind the mill. And you'd get this weird pattern on one side, and then all of a sudden it becomes really choppy with ridges or a strange elevation. So if that were to occur, it would be very, very obvious. You wouldn't need a grade checker to determine that, although that would still catch it as well because you're checking right behind the machine. But you'd see it quickly in the pattern of the machine. Anyone? Oh, go ahead, Grant.
Yeah, and I guess I'm also thinking of it as you're approaching what you're trying to correct in terms of, like, just hypothetically, if you were trying to get, say, a 2% cross slope across the machine, but in the center you wanted it to go a little bit further down. Like, is that possible where the teeth in the center could be deviating from that constant cross slope across the machine?
Gotcha. Okay, that makes sense. So to answer that question, no, it's not possible for the width of the drum to deviate or change, have a slightly different slope on one side than the other. It's a solid line, right? So it can only go like that. But what you would do is if you have a break in your cross slope, then you take one pass at where that break is, and you have a grade going that way. You may take another pass on this side and change the elevation going the other direction. So at some point you may have a short pass. You just have to make sure you plan that appropriately, and you may be only milling 4 feet and it kind of extends out into somewhere where you've already been. But that's all you would need to do is just take a shorter width pass and have a starting point, one edge of that machine at wherever that break and cross slope is. And that could be at center line or something too. That happens all the time. So you wouldn't want to straddle center line in that case. You'd want to start at center line and move your way either direction.
Okay, yeah, that makes sense. I have an upcoming project where we're going from a super elevated surface and installing a large feature that will essentially create a crown there. So it'll be like a pretty significant deviation, which doesn't necessarily involve the scenario I was asking about, but understanding, I guess, where those limitations of the machine are does help me conceptually see how that could be achieved.
Sure, and that's
Thanks,
just kind of planning, making sure that you decide where your passes should be ahead of time so you can incorporate any of those slope breaks. Anyone else? Are there any other questions or comments or thoughts out there? Okay. Well, obviously, if there is, feel free to shoot me an email and then we can answer back. We can have a conversation, certainly more than open to do that. Even if, it's just information gathering, we're more than happy to start those conversations. So once again, I want to thank everyone for joining us. We wish we could have been on site, but it just didn't work out. So thank you for your time and appreciate everyone.